All right.
Hello, everyone.
Yes,
my name
great.
is
You can hear us? Oh, pre-recorded. Oh, okay. All right. I didn't know that. Okay, sure. Then just play it.
Ismail Kuru. I will be presenting our paper, Modal Abstractions for Virtualizing Memory Addresses. So let's first discuss virtualized memory from systems perspective. So virtualization is a common concept that appears in multiple different systems design, but for memory virtualization, we can concretize the practice of using it as a virtual pointer pointing to a physical page. I mean, supposedly allocated physical page. And memory virtualization, as most of other virtualizations, are done for creating the perception of abundance. So memory virtualization basically creates the deception of having more memory than we actually have. And memory virtualization is realized in an well-known abstraction called address space. We can think of address space as a named container for virtual to physical memory mappings. So the core mechanism realizing the memory virtualization is called address translation, and it's implemented with data structure called page table trees, or like sparse page table entry trees. Here is in the middle we see 4 levels of tables realizing a sparse page table tree. At the top we see a virtual address including indices to each level of this tree, and here at the bottom there's a unique root address to that tree. And basically the traversal is traversal basically starts at the level 4, top level, and each time for the next level we calculate the next level's table's address and get the index for that table's entry from the virtual address, and then access to that entry. And when we are done with each level, we will be finally reaching to the physical page. Here we see a rough outline for the address space abstraction. At the top we see designated control register CR3 pointing to the name of the address space root, which itself is a unique root address of the page table tree of this address space, which sits in between virtual addresses and physical addresses, VA and PA. And when this designated control register points to an address space, then the current view of the memory basically becomes the memory layout of that address space. So why we care about virtualized memory? We care about it because it's one of the core pieces in the kernel that provides resources to the rest of the kernel, pretty much to the complete rest of the kernel. And we think that when we understand this piece rigorously and mathematically, we will be able to understand the rest of the kernel more properly. So before getting into the mathematics of virtualized memory, we should speak about some important aspects of virtualized memory. So here we see on the right a function at the bottom, Rocq page directory. It's basically implementing the address translation, like traversal of the page table tree, which calculates the root address of the next table, and then get the index to the entry for that level from the address from the virtual address. And if that entry does not exist, then basically it allocates and puts it in there. So it modifies, it changes the shared physical page table tree, page tables. So this is important because, like, if this is done without following any protocol, like accessing and mutating these shared physical page tables would cause all the other virtual to physical memory translations in the same address space to be invalid. So up until now, we were inside the address space. But now if we take a step back, we will see that there are multiple address spaces in the kernel, and these are like managed by the component called Virtual Memory Manager. And one of the most essential functionality of Virtual Memory Manager is basically switching in between address spaces. And it's basically loading the address space name or identifying piece to the designated control register CR3. So here we, as we see on the top, inline assembly, it's basically one instruction, one move instruction, loading the CR3. Now we have pointing the root I with the CR3, and then we will switch into the root J by loading root J to it. So now, okay, now we can look at the virtualized memory from the logical perspective and understand the verification challenges that it exposes. So first, since our assertions for the virtualized memory are in separation logic, we should take a quick recap on separation logic assertions. Most importantly, the most crucial one in our context is called points to assertions, or like named ownership assertions, like memory reference points to a value, like heap value. So these we can think of them like as a token to an as a logical token to an underlying physical resource. So they can be either fragmental tokens or fully owned tokens, where the full ownership grants the access to change the underlying resource associated with it, and fragmental would give you the non-mutational accesses. And so on top of our machine semantics, defining the register points to and physical memory points to were straightforward. But as you might have already noticed, like virtual points to is a little bit tricky. So a naive attempt to define the virtual points to relation would be like giving a definition to it by in terms of like unfolding physical points to assertions describing the accesses to the shared page tables at each level. However, as we discussed briefly before, like this assertion would not be sound under the existence of any virtual memory action mutating the shared page table, which we already saw, which we already spoke about. So we need to find another way. So what we propose is to define the virtual points to relation in two pieces: traversal of the page table tree and access to the underlying physical page. The traversal piece is abstracted via a fragmental token summarizing the traversal of shared page table, and these tokens are distributed to all virtual points to relations in the address space. So the second piece is, as expected, like is fragmental physical points to the physical page to look up the to read the physical page so by having this kind of form, we basically recover the soundness of address translation, because when the protocol enforces having the full ownership of the traversal token to change the underlying shared page tables, which resides inside a persistent invariant. So after fixing the problem on address translation, now we can focus on the address space management. So we know that virtual to physical mappings are only valid in a certain address space, but we can never infer this from these mappings because they are unaware of the address space they are in. So we reflect this fact into our assertions by lifting the relevant propositions, which we call VPROPs, with the unique identifying root address of the address space, and then we relate the address space with its virtual pointer relations in a modality called address space modality. Here we see P rooted at R, asserting that all the virtual pointer assertions in P are valid only under the address space identified with R. So let's pull things together. We spoke a lot. Let's pull things together in an address space switch example. So here we see two address spaces with the root addresses root I and root J, with virtual address mappings for the addresses VAI, VAJ respectively, and currently loaded memory is root I's memory, as the control register is loaded with it, is pointing to it, and as we see in the precondition, root I's virtual mapping is loose in the specification, but root J's is under the address space modality. So, but when the address space switch happens, CR3 is loaded with the root J's name, and then name root J, and then the mappings of root J address space will be loose in the specification in the post condition, and root I's virtual mappings will be put under the modality, address space modality. So it's a neat, clean specification of an address space switch, but I think it's worth highlighting some of the subtle aspects in this specification. So we have the resource context duality in here. What I mean by saying that is basically we have two address spaces mentioned in this specification, which is either the current one or the one to be loaded into the control register. So this duality allows us to have the luxury of not annotating the virtual pointer assertions with the root address space names, like VAI points to PAI does not include that. That form of this assertion does not have any naming related to root I. So this is pretty much what I would like to say. This is a gist of what is in the paper. So there's a lot in the paper. There are more other critical pieces of VMM discussed in the paper and verified, and subtle aspects of kernel invariant is also in the paper, and large soundness proof is also in the machine. We have a huge machine check soundness proof for our machine model, and also we have some discussion on the on our machine model in the paper. So right now this is the end. I'm on the postdoc job market. If you think that I will be a good fit into your research context, then I will be grateful if you reach to me. And now I'm happy to take questions. Thank you so much.